Alrighty, hello everyone, and welcome to Cafe Scientifique from all of us here at SFU's Faculty of Science. My name is Stevie Benish, and I'm the Manager of Outreach and Engagement. And if you are one of our cafe regulars, welcome back. And if you're new here, well, welcome for the first time. We're so happy to have you with us. So tonight is actually our last talk of our spring 2026 series, and we are very excited to be wrapping it up with such a fun topic. For those of you who don't know, Cafe Scientifique is our public seminar series where our different presenters share their current research and its impact for the local communities and for kind of society at large. So we generally have about six of these discussions a year. They're all online and they're also all recorded. So if you have missed one in the past, you can always go back to our website and check them out. Or if you'd like to share this talk with somebody who wasn't able to be here tonight, you are able to do so. And we'd always love to hear from you. So after this talk, if you want to reach out, please feel free to do so. We always love to hear kind of any thoughts you have about upcoming topics you'd like to hear or feedback on the talks we've already had. So before we get started, I just want to start us off on a good way by acknowledging that I today am very privileged to be joining you from the unceded and ancestral lands of the Musqueam, Squamish, Tsleil-Waututh, and Coquitlam peoples. And I hope you all take just a moment right now to also just think about whose land you are joining us from today. And if that is something that you're not sure of, I'd like to share a great resource we have. Um, it's native-land.ca, and it's a great place you can go and familiarize yourself with the Indigenous peoples whose lands you are lucky enough to live and work on. Okay, before I pass it over to our amazing speaker, just a couple details to go through. So, as I mentioned before, this talk is being recorded and it will be shared. There is a live transcript available for your convenience, and the chat will be turned on. So if you have any questions, we will have a Q&A period at the end, but feel free to drop any questions both in the chat or in the Q&A box throughout the talk, and we will get to all of those at the end. Alrighty. Now time for what we're really here for, tonight's discussion. So I'm very pleased tonight to be introducing Dr. Dan Gibson, who is professor and departmental chair in the Department of Earth Sciences here at SFU. So Dr. Gibson is interested in crustial processes associated with mountain building events, and his research is both field and lab intensive, and it involves bedrock mapping and sample collection for structural, petrological, and geochronological analysis, typically exhumed from deep crustial levels within the core of a mountain belt. And tonight, we're going to be led through a journey of the awe-inspiring mountains of British Columbia. And we're going to be exploring the geological processes that formed one of Earth's most impressive mountain systems and shaped the amazing landscape we are so privileged to see today. So, without further ado, over to you, Dan.
Thank you very much for that very nice introduction. So let me get that. Right. Well, it's a real pleasure for me to go over the mountain building history of British Columbia because, in my opinion, it is one of the most awe-inspiring and probably, in my opinion, as well, the best mountain belts on Earth. Um, there's nearly 1 billion years of history embedded within the mountain system that we have within British Columbia, but also within Alaska, Yukon, and the rest of the Western US. So what they call the North American Cordillera. I've only really got about 45 minutes, so you're going to have to buckle up your seatbelts because we're going to get through about 1 billion years of history. And I'll try to do my best to make it as fun as possible and as comprehensible as possible. And so, whence the mountains? So that was a, a question that was asked a long time ago when geologists were first, trying to understand how these big mountain belts are formed, the Himalaya, the North American Cordillera, the Alps, the Urals, the South American Cordillera. And so, sorry. There we go. There are a couple really essential things that you need to know about how mountain belts formed. Okay, so one of the things that you need to know is how were they made? Most specifically, what's the physical processes that were involved in their development? And then the other very important part of it is when were they made, right? So you need to know the sequence of how things happened and when things happened. And so you also want to know how long did it take and at what rate did it happen? And so my research, it's, I guess, what you consider multidisciplinary. So as Stevie indicated earlier, I do quite a bit of field work. I go out there with students through the years and we collect information, understanding what rock types are out there. For me, the structural geology, so that's understanding the types of deformation that the rocks have undergone, whether it's faulting or folding or other styles of deformation that have led to their current form as we see them today. Now, I also do igneous and metamorphic petrology. So that's basically looking at the rocks and understanding, what type of rock it is, how it's made, what's its chemical composition, what did it come from? Was it from a melt or was it from erosion and then lithification of sedimentary rocks? And then I also do quite a bit of what's called geochronology, and that involves looking at minerals like zircon here and looking at their isotopic characteristics, especially uranium and lead, because we have a very good idea. They're very precisely, we know the decay rate of uranium isotopes to their stable daughter product lead. And so knowing that, we can calculate how old that zircon is fairly precisely, and then we can use that to, give us an idea of when certain rocks were formed or different magmatic bodies crystallized or different deformation processes um, were underway. And then we take all of this information and we weave it into a tectonic model, trying to understand tectonically what happened in the past to lead to what we see today. It also involves quite a few methods, the field studies with students and other colleagues. So through the years, I've been very fortunate that I've had lots of people help me gather information, and I've leaned on a lot of previous work that other people have done through the decades. So this is really putting together a lot of different information from a lot of people, and a special thanks to all my students that have helped out with this. And we'll take that information and samples from the field and we'll do lab analyses on it. This is a thermal ionization mass spectrometer. That's how we get the isotope characteristics of things like zircon to get those ages that we want to get. Electron microprobe, this gives us information about the chemistry of minerals. It also allows us to see at the nanometer scale the characteristics of these minerals. And then this one down here, a laser ablation, inductively coupled plasma mass spectrometry. It's a real mouthful, but it's also another type of method that we can use to analyze zircon and other minerals to give us the ages that we want to use to constrain the processes that we're trying to understand. And then also, my research involves multiple scales. So, mountain belts, of course, you want to look at it from the perspective of a mountain belt. So, you start at that scale, and then when you're out there, you get down to the outcrop scale and you look at things more closely. And then you can take samples from the outcrop and you can bring them back to the lab and you can make them into rock thin sections, about 30 microns thin that allows transmitted light to come through it. And you can look at it in a microscope and look at it at a scale of millimeters to micrometers. But we can also take those thin sections of rock, and other pieces of rock samples and look at them in other imaging with other imaging techniques like a scanning electron microscope that we have here to give us down to the nanometer scale of imaging. So we take all of that information from multiple scales, from multiple disciplines, and that helps us to understand how these mountain belts, in particular for me, the Canadian Cordilleran Mountain Belt, form through time. And so I guess a question, that you could ask, and I have been asked this before, is why study how mountains are made, right? And to me, it's like because they're there, right? For sure, that's one thing. But they also are one of the most fascinating things for me on Earth. I want to know everything about them. I obsess about how mountains are made. And part of the reason for that is when I was a kid, I grew up on a farm in southwestern Manitoba. It was a beautiful place, had a great childhood on the farm, but it was flat as a pancake, just dead flat. And so you could see for miles, and the sky is huge. But it was something that when I was a bit older in grade 7, we went on what they call a Rockies trip. And so they take the grade 7 and 8 kids from this little farming town in Manitoba, stick them on a bus, and you drive through the prairies, the monotonous prairies, flat, flat, flat. And eventually we get to Calgary, and I'm beginning to nod off because it's a long bus trip. And then I hear some oohs and ahs and people remarking about something. And I wake up and I look out the window and I'm absolutely floored. I cannot believe what I see. Just this wall of mountain in front of me. And I could not fathom how that could have happened. We went from the dead flat prairies into Calgary, and suddenly we see this just unbelievable mountain right in front of us. And that to me was the hook. That forevermore, I just needed to know how that happened. And so I'm hoping today that I can provide for you some of that information that, will help you along the way like it did for me. And so here we have a false color image. I like this image of the Canadian Cordillera. It also includes Yukon up here and Alaska as well, southeastern Alaska. But it really exemplifies the dramatic topography of the western part of Canada, right? And so it's a significant part of Canada. It's 16% of Canada's land mass that is encompassed within the Canadian Cordillera. And so it's really important for many reasons, to understand how and when they were made. Um, just to give you a sense of the grandeur of the North American Cordillera and the Canadian Cordillera specifically, on the left here is a global image showing, the North American Cordillera along the western margin of the North American plate. On the right here, this is focused in on the Himalayan mountain belt. And so I have some colleagues that work in the Himalaya, and they tease me about, oh, how small the mountains are in the Cordillera, and they're nothing compared to Everest. And then I bring up the fact that just in British Columbia alone, in the Canadian Cordillera, it's 3 million square kilometers of land mass, about 16% of the country's land mass. Whereas the Himalaya, that's a measly 595,000 kilometers of land mass, squared land mass. So I think that's one of the reasons why I think the Canadian and North American Cordillera is the most impressive mountain belt in the world. So let's start off with what we know as far as, what's going on now and how that, gives us information about how the Canadian Cordillera, the mountain system in British Columbia was formed. So we can see here, this is the current configuration of the plate boundary between the North American plate here on the right and the Pacific plate on the left. And where we are in Vancouver here, just outboard of Vancouver Island, about 100 kilometers west offshore of Vancouver Island, is what they call the Cascadia subduction zone. And here, a very young and relatively warm oceanic plate called the Juan de Fuca plate is going down, subducting down beneath the North American plate, basically beneath our feet. It's probably around 80 to 100 kilometers beneath our feet by the time it's beneath Vancouver. And then we can see here there's also the San Andreas strike slip fault system, or transform fault as they call it in plate tectonic terms, and the Queen Charlotte fault system. Now, what I'd like to focus on here is the Cascadia subduction zone. So at one point in time, this subduction zone, which causes compression in the overriding plate. So it's called a convergent margin because the two plates are coming together and converging against each other, with the oceanic plate being more dense and going down beneath the less dense North American plate. Now, for about 200 million years, give or take, this has been the configuration along the North American margin, except for the fact that it was largely a subduction zone. We didn't have these strike slip transform fault zones. It was largely a subduction zone. And here's, just to give you a better sense of what it looks like in three dimensions. Here's the Juan de Fuca plate. It's coming down beneath the North American plate. Water is coming off. It's driven off the sediments and some of the rocks within the crust of the Juan de Fuca plate. And that water acts as a catalyst. It's almost like a flux. Well, it is a flux really that causes melting within the mantle here that's above the Juan de Fuca plate. And that melt makes its way up and gets embedded within and erupts onto the North American plate in what they call a, a magmatic arc or volcanic arc. And I'll come back to this near the end of the talk to look more at the volcanic arc that we have here today. But just to give you some sense of the forces that are involved and that relate to how do you push up, giant blocks of crust to create these mountains? Well, if you think of it in terms of pressure in what they call pascals, the plate collision at a convergent margin, a subduction zone, in other words, generates immense amounts of pressure in the range of 0.2 to 1 billion pascals. Now, if you're not familiar with those terms, I can put it in other terms that might be more familiar to you. That's equivalent to about 10 to 100 trillion heavy-duty bulldozers pushing simultaneously against the North American margin. So that's a lot of force that's involved in the compression that causes the uplift of these mountains. And so, as I mentioned before, this has been going on along the western margin of North America for a long time, for about, give or take, 200 million years, almost since the time the Atlantic basin began to open up, and you had Western Africa and Western Europe basically rifting away and moving away from the east side of North America. On the west side, what was happening was there was consumption, subduction of oceanic lithosphere. So the Paleo or Proto-Pacific basin was subducting underneath the western margin because the Earth is not growing. So if it's growing in the Atlantic basin, something else has to be consumed. And so on the western side of North America, that's where we have and still in part have subduction going on, where oceanic lithosphere is going beneath the western margin. Impressively, over about 200 million years, that's led to about a third of the Earth's circumference to be subducted below the western margin of North America. So that gives you a sense of just how much subduction, how much of the Earth's crust or lithosphere has gone down that subduction zone. And while that's happening, that ocean plate is acting as a conveyor belt. So you have you see these high standing spots. There's Hawaii, but there's the various atolls and whatnot that belong to the Hawaiian and Emperor Seamount chain. If those collide with the subduction zone, they're high standing, they're less dense typically, and they get scraped off and what they call accreted onto the overriding plate. In this case, it would be the North American plate. And so that's been going on for a better part of 200 million years. And so that's led to a growing out of our western margin where you've accreted on these bits and pieces of island arcs and oceanic plateaus and other high standing features that got ferried in on that oceanic subducting plate and accreted onto the western margin of North America. So this is going to be a giveaway for what I'm going to talk about for the rest of the talk. So this is the Canadian or North American Cordillera is referred to as an accretionary mountain belt in that we have in the beginning, it was along the western margin, a passive margin, in that very much like what we have along the eastern margin of North America today. There was no subduction zone. It was just a oceanic lithosphere basically transitioning into continental margin. And so it was nice and stable and passive. That's why it's called a passive margin. And then at about 360 million years ago, for reasons that I can't get into because it would take way too long, a subduction zone initiated off the western margin of North America. And it was a little bit, not quite right at the margin. There was a little bit of ocean in between. And over time, that subduction zone, we go from 360 million years ago to about 190 million years ago. Some of these magmatic arcs that were developing out in the oceanic system above this oceanic subduction zone eventually make their way and get accreted onto the western margin of North America. And so there's multiple terrains. They call them terrains. They're fragments of the Earth's crust that get scraped off and accreted onto the western margin. And through time, that builds out the margin to the west. And it also leads to the development of the North American Cordillera from about 190 million years ago to about 50 million years ago. That was the main phase of mountain building. There's still some mountain building going on in the North American Cordillera, like up in Alaska and Yukon with the Denali and Mount Logan, the highest mountains in North America, are the result of uplift above a subduction zone where a microplate is getting stuffed underneath Yukon and Alaska, causing a lot of uplift there. And we've also got uplift going on right here because of the Juan de Fuca, subduction of the Juan de Fuca plate. And so what we have today is the mountain belt that we see. We still have some subduction going on, but a large part of the margin now, at least for British Columbia, is strike slip with the Queen Charlotte fault system. And we've only got a small part where the Cascadia subduction zone affects the mountain system in that it's still causing some uplift today. And so this long history of having terrains, these fragments of oceanic and continental crust being accreted onto the western margin of North America has led to what they call, or we call, the Cordilleran collage. And so all of these colors in green and purple and pink and a bit of gray here, these are all pieces of crust or lithosphere that has been tacked on to the western margin of North America since about 190 million years ago. So the previous margin is, somewhere well to the east of us, before all of that accretion occurred. So now I'm going to take you on the Cordilleran time machine, and I'm going to ask you to strap on your seatbelts because this is going to be a fairly quick overview of the mountain building history in British Columbia, but I'm going to back it right up to 1 billion years ago, and then we're going to work our way forward. So about 1 billion years ago, there was the supercontinent Rodinia. So there was a number of different plates that had come together to form the supercontinent. And the supercontinent was basically centered near or on the South Pole of Earth at that point in time. And so that's why we're looking at what's called a South Polar view, just so we can see, the better part of Rodinia. If we had a North Polar view, we'd pretty much only see ocean. And in this, at least this rendition of what Rodinia looked like, here's North America. That might have been Australia. We're not quite sure. It's really hard to know what was attached up here before it rifted away. Baltica or part of Eastern Europe was over here. Bits and pieces of the African continent were here. Here's India. And so if we move forward in time to about 700 million to 650 million years ago, this is when North America began to break away. Rodinia was rifting apart, and North America began to break away from those other continental pieces. And this is when North America kind of became its own entity. And if we move forward a bit here in time to about 540 million years ago, North America now is this continent. It has a passive margin on its western margin and eastern margin. So it's really quite happy. There's no subduction zone causing stress and pressure on the western margin of North America. It's nice and passive and there's sedimentary rocks being deposited along there. All sorts of nice things are happening to it at this point in time. I include this slide to give you a sense of what the rifting was like. So as that Rodinia continent was rifting apart, there are certain types of sediment that we know that we can identify in present day rift settings, like the East African rift system. And we look at the character of those sedimentary rocks and magmatic and volcanic rocks that you find in these rift systems. And we can compare it against some of the strata that we find within the mountain belt here in BC. And we can see at about, 600 million years ago, there are rift strata. And so we know that the margin rifted at around that time, that we find these volcanic rocks, we find these sedimentary rocks that are very characteristic of a rifting environment. You're tearing the crust apart and things are falling into that rift zone, just like the East African rift today. And so that's how we know that and when it was rifting and the style of rifting that was occurring. And so eventually North America was, sort of, here's Greenland as well. So it was still attached. It was happy to be part of, it would have been part of Canada, not the US. So it would be happy in that position, I'm sure. And so here we see North America. There's a passive margin here. Actually, the eastern margin did have a convergent subduction system. So it's kind of flipped compared to what we see today. And out to the west here was a massive ocean. It's kind of like the Paleo-Pacific or Proto-Pacific Ocean basin. It was called Panthalassa, the Panthallassic Ocean System. And it was massive. It went about 2/3 of the way around the globe from the western margin. And so this is at about 500 million years ago. We're going to go forward in time here and skip to the point where the actual mountain building kind of begins. At about 400 million years ago, a new subduction system formed outboard of the western margin of North America. And it's really hard to know with certainty what caused that subduction system to form. It's actually very difficult to form a subduction system. We don't have any modern analogies that we can use that we can look at where one is forming today. And so it becomes a somewhat speculative, I guess, and lots of people do, computer modeling to try and model it, but it's still a little bit of a mystery how it formed, but let's just take it for what it is. And it formed around 400 million years ago, based on evidence that we see for the magmatism, along the volcanic arc that forms above the subduction system. We can date that, and we have a pretty good idea. It was around 400, 390 million years ago. And then I should point out here, in between is still a seaway, an oceanic seaway here that's separating this new subduction system from the actual western margin of the North American continent. And so if you took a look at what we call a cross section, a three-dimensional view here of that subduction system, what we see is that there is the subduction of the panthalassic ocean floor here, or the oceanic lithosphere, beneath what would be the westernmost, extent of the North American tectonic plate. That would be in the upper plate above the subduction zone. And new volcanoes and magmatic systems would be produced above that subduction system. And we see, and we see evidence for that further inboard where, when volcanoes erupt, they'll have clouds of volcanic gas and volcanic debris, and some of that gets carried in the atmosphere and then deposited on the continent here, and then looking at how old that is and ascertaining how close or how far it was from that subduction zone gives us the information that allows us to make this type of interpretation. And so jumping forward quite a bit here from about 400 million years ago to 190 million years ago. So we see here that this subduction system is getting closer to the western margin here. This seaway that's here is beginning to close, and there was likely another subduction zone inboard here that was causing this ocean part of the ocean basin to be consumed and bringing closer these terrains. And we'll just call them the inboard terrains. They're the first ones to get accreted onto the western margin around 190 million years ago. But I'll bring to your attention these more outboard terrains here. So they're still out in the panthalassic ocean system, and there's probably another subduction zone out there that's feeding the volcanism and the growing of these volcanic islands out in the panthalassic ocean system. These will come in a bit later in time. So we're at 190 million years ago, and we go and take a look at the cross section again. And so this is the idea here that you've got this subduction zone. You've now had the accretion of these inboard terrains. They're getting fully tacked on to the western margin. And at the same time, this is important to note, North America is moving westward. And that is related to the beginning of the opening of the Atlantic Ocean basin. So this is now the rifting of another supercontinent, Pangaea. And as Pangaea was rifting apart and Western Europe and Africa are beginning to move to the east away from North America and South America, North America moves westward, and it's actually causing an impingement against the subduction system. So as the oceanic lithosphere here, the oceanic plate is subducting beneath North America itself is moving westward and pressing against that oceanic plate. And that in turn causes an accentuation or increase in compressive stress on the North American plate that leads to uplift and leads to mountain building during this time. And so at about 175 million years ago to about 100 million years ago, with continued subduction, continued compression because North America is pressing against that subducting oceanic plate, this is a major phase of mountain building in the North American Cordillera. And so a big part of the BC mountain system was being developed during this time frame from about 175 million years ago to about 100 million years ago. And at about 100 million years ago, then that second system of ocean islands that were more outboard are now beginning to dock onto and accrete onto the western margin of North America. And we can see here at this point in time too that the Atlantic Ocean basin is full, full on. It's not near its maximum width, but there is full separation of Western Europe, of Western Africa from North America and South America. There is an incipient rift zone coming through here that's beginning to split Greenland away from North America. That will eventually die out and stop. And so, in fact, Greenland is actually still a part of the North American plate. It's not fully rifted away from it. So if Greenland ever wanted to claim that they're a part of Canada, we could do that. It's fully within our geologic realm to accept Greenland as part of North America. Another really interesting part to take note of here is that we have the buildup of these accreted terrains and the buildup of the mountain system along the western margin of North America, and in particular here in British Columbia. And that is causing a significant load on the lithosphere, on the North American lithosphere. And so that load is causing a downwarping of the North American lithosphere here. And so in front of that downwarping, we're getting the ingression of an interior seaway. It's sort of like if you took a board and you put a big load on it and you begin to warp that board down. In front of the warp, you're going to have this trough, this low standing area, and that gets infilled here. It goes below sea level, and it develops a seaway out in front of the mountain system here. So this interior seaway is out here in front. Here's the mountain system that's developing. It's causing a downwarping of the lithosphere and a trough, effectively a trough in front of the mountain system to the east. And there's sediment that's coming into that trough from the east, from the Canadian Shield, but also from the emerging Cordilleran mountain system is also shedding material into that trough. And that is referred to as the foreland basin. And that will become a very fertile system because it gets a lot of organic debris in it, and it becomes the petroleum bearing units that we know today that Alberta is so richly endowed with. And so by about 75 million years ago, there is a full development of the interior seaway because now we've got, in large part, the mature North American mountain system or Cordillera developed here. And that's causing a warping down, a weighing down of the western side of the North American plate. In front of that down warp, we have this trough that the seaway comes through, and it went all the way through. We know this. We see the sedimentary deposits of this time frame around 75 million years ago. And we see that it went the entire length of the North American continent here. And we go forward about another 25 million years to about 50 million years ago. And this is when the Cordillera, the British Columbia North American Cordillera, was at its peak. There would have been a large plateau So if you look at the Tibetan Plateau in the Himalaya or down in South America, there's the Altiplano Plateau. It would have been similar in size and height as what they have today in the Altiplano and in the Tibetan Plateau, around 5 or 6 kilometers above sea level, and fairly consistent from the margin right into the interior here towards Alberta. And so that plateau system, of course, gets carved up later on by erosion and especially by glacial processes that I'll talk about in a little bit. And so at about 50 million years ago, the convergence between the oceanic lithosphere subducting beneath the North American plate and the westward movement of the North American plate, it changes its trajectory. And so the oceanic lithosphere changes to a more northerly trajectory relative to North America. And so that relaxes the forces along the western margin. And so you're no longer having significant uplift. In fact, a lot of the mountain belt begins to relax and extend and lower itself because it can't support, you don't have the forces to support that high standing mountain system anymore. And then we go forward into the late Quaternary here, about 20,000 years ago, and this is when we have a significant ice age, a large ice mass is covering a large part of Canada here and down into the north and northeastern part of the United States. The Cordillera has a Cordilleran ice sheet that's also around 2 kilometers thick and is you know covering most of the Cordillera, except for little bits and pieces of peaks that might have been poking up through it at the time. And so that glaciation and climatic processes that follow it during the melting of the glaciers, they're still melting today, of course, has led to the carving out and production of this beautiful landscape. So we had about 2 million years of tectonic processes, terrain accretion, subduction zones causing compression on the North American western margin, the uplift and building of the North American Cordilleran mountain system. And then very recently, like in a heartbeat, the glaciation occurred around 20,000 years ago. It eventually a lot of it's melted away, receded away, but the glaciers have left behind, just an amazing landscape of carved mountains for us. And so this is what we're left with today at present. We have the beautiful BC Cordillera here with many fjords, beautiful fjords along the western coastline here that are largely due to the influence of the glaciers carving those fjords up for us. And there's still high standing mountains. Of course, we see them. Part of that is due to the subduction of the Juan de Fuca plate beneath Vancouver Island and beneath our feet. But also another part of it is that the lithosphere is now quite thin beneath this part of the Cordillera. And that causes the really hot asthenosphere beneath our lithosphere to be much closer to the surface than it would be if it were, you look beneath the Canadian Shield that has a lot older, colder, and thicker lithosphere. And so that hot, buoyant asthenosphere that's closer to the surface here is helping to buoy up a large part of the Cordillera still. And so I'm just going to take you on what I call the Cordilleran time machine. And hopefully it doesn't cause you too much turbulence and you don't get motion sick here. But I'm going to run a little video that goes over what I just talked about. Oh, yeah, let's see. And so here we're back in the Paleozoic, and we can see these island arcs offboard, and they're starting to get close and starting to accrete. Here's the outboard terrains coming in, and they're starting to converge upon the Cordillera. Here is the Cordillera in its peak, its glory. We hit 50 million years ago. The plate trajectories change. We come up to the Quaternary. There's the Ice Age, and we were left off with that modern present day landscape of the BC Cordillera. Okay, so one other thing I'd just like to touch upon before I end off here is, that's fascinating. Like for me, that is like the raison d'etre for why I do my research. I want to know how those mountains were built, when they were built, how long did it take to build them, what the processes were involved. Um, but why else is it important to understand this? Well, we are living on the edge. In this region, we're right near a subduction zone, the Cascadia subduction system. And so we need to be fully cognizant of the geohazards that presents for us. That includes the volcanoes, those magmatic or volcanic arcs that come up above the subducting oceanic lithosphere into the upper plate where we are. There's earthquakes. So I'll show you in a second here the generation of earthquakes because you have the North American plate pressing against the Juan de Fuca plate. And that locking up between the two plates causes a buildup of a lot of stress. And when that stress overcomes the resistance, the coupling of the two plates, that's when we have these big mega thrust earthquakes. And that leads to other significant issues like tsunamis and landslides that we need to be aware of. Another really important facet that goes along with understanding how that mountain system developed is that BC is really richly endowed with ore deposits, especially what are considered to be the critical minerals: gold, silver, copper, um, you name it, we've got it. There's a lot of critical minerals in British Columbia, and in large part, it's thanks to that mountain building evolution through time that has produced these very fertile pieces of continental crust that host these ore deposits. So coming back to the hazards, I'm sure everybody's heard the term the Ring of Fire. And here we are up in Vancouver here, the Juan de Fuca subduction system. And we need to be quite cognizant of the fact that we are part of this ring of fire that basically rims the Pacific basin. So wherever you see the bright orange kind of fiery parts here, that's where there are subduction zones and convergent margins between overriding plates and subducting oceanic plates. Here in this region, we've got an active volcanic arc. We've got Mount Meager that has been active in the relative recent past. Mount Garibaldi, very recent volcanic activity. In fact, there's a lot of volcanic activity going on today that we need to be monitoring. Down in the US, we see Mount Baker there. That's also a volcanic center that we need to keep an eye on. Mount Rainier further to the south, and Mount St. Helens. If you're around in 1980, I think you all know about Mount St. Helens and the devastation that led to when it erupted. And here's just to give you an idea, just to refresh your memory. In May 18th, 1980, I remember this clearly. I was a kid on a farm in Manitoba, and this plume came over Manitoba and deposited ash in Manitoba. And so it was a pretty significant eruption. The eruption column rose 80,000 feet into the atmosphere. And the thermal energy that was released during the eruption was equivalent to about 26 megatons. Here's, oh, sorry. There we go. Here's Mount St. Helens before the eruption, and here is Mount St. Helens after the eruption. And you can see how much of Mount St. Helens is missing after that eruption. So I don't want to be Chicken Little here and say that we're doomed, but I'm saying we need to have earth science literacy and be on top of monitoring these things, be aware of what's going on beneath our feet and on the surface. Also, when it comes to the seismic activity and the earthquakes, this is a bit of a complicated diagram, but here's the Juan de Fuca plate. Here's Vancouver Island, Victoria, Vancouver. The Juan de Fuca plate's going underneath here. That's the subduction zone, and it's going down underneath us. This is causing compression on the western margin here, such that Victoria is actually getting pushed at about 7 millimeters per year towards Penticton. And so here's kind of like a cartoon that I put together that shows the Juan de Fuca plate coming underneath the North American plate. You've got the North American plate pushing westward against the Juan de Fuca plate, which is young and buoyant. And so those two things lead to a locking up of the interface between those two plates. And it's causing uplift of Vancouver Island. So Vancouver Island right now is uplifting. And in between here, the down warp is the Georgia Basin that we have to take the BC ferries across to get to Vancouver Island. And then here's the North American plate where we're situated. When that unlocks, this warping here instantaneously releases like an elastic band. And that causes a big, what they call a megathrust earthquake. And we know that those happen every 300 to 800 years ago, on a cycle of every 300 to 800 years. On average, it's about 500 years. And the last megathrust earthquake was about 1700 years ago, about 400 years ago. So or not quite 400, we're kind of due for one of those big earthquakes. So we need to be prepared. We need to have things, prepared and monitored and understand what we're dealing with. And this is just I give you an idea of recent earthquakes, and the bigger the kind of red star shape here, the bigger the magnitude. So this big one here, that would be got cut off, but it's about a magnitude 8 earthquake, and that said was about 1700 AD. And so, but we've had other ones that have led to, smaller earthquakes. They're fairly common out here. Some we don't even feel, but they're an ongoing issue that we need to be cognizant of. And with earthquakes and also deglaciation. So as the glaciers melted and retreated, they leave oversteepened valleys. And these oversteepened valleys become unstable and can collapse, especially if you've got shaking of the ground from earthquakes. And so this is a photo of the Hope Slide that, I think if you have traveled along Highway 3, you've seen the Hope Slide, and this was before they cleared all the rubble away from the collapse of the Hope Slide. The last thing I want to touch on are the ore deposits within British Columbia. like I said, we're richly endowed with these deposits. There's about 17 operating mines in British Columbia and hopefully more. And this is thanks to that prolonged history of deformation and magma generation related to the long-lived subduction zones along the western margin that represents a very fertile environment for the concentration of base metals like copper and zinc and precious metals like gold, silver, and platinum. And so British Columbia is the envy of the world. And that's why in Vancouver, we've got one of the biggest exploration and mining centers in the world. And this is what I call the Cordilleran Metal Factory. And it just gives you a very quick and dirty idea of the different deposits that can be formed at a convergent margin, like the one we had for the past 200 million years along the western margin of North America. You can have magma coming in here and the porphyry, copper, gold, and molybdenum deposits. There can be volcanogenic massive sulfide deposits that are more peripheral to it. If you have limestones and there's interaction with magma, you can have skarns that get very rich in base and precious metals. Epithermal gold and silver deposits that are related to further afield, higher level magmatic activity. So through time, you can imagine that, that continuous process of subduction and magmatism has led to a very richly endowed and fertile continental piece of crust in British Columbia that we can see here. I'm not going to go through all of this, but this just gives you an idea of various deposits within British Columbia and some of the active mines that you can see with the two pickaxes crossing each other. That's where active mines are. Uh, and I'd just like to point out that there's more than 35,000 jobs in the province that relate to mining and exploration with an average annual salary of $135,000. So it's quite profitable, obviously. And the industry itself is accounted for about 30% of the province's exports in 2024 and had a total economic impact of $18 billion. So thank you, the Cordilleran Mountain System, for providing that for us. That's been a tremendous little spin-off from the mountain building history that we have in BC. And so at that point, I'd like to thank everybody for persisting with me. And if you have any questions, I'd be really happy to answer them.
Wonderful. Thank you so much, Dan. That was incredible. We do have a few questions already. Our first one was actually about gold deposits, and I think you already answered it. So we'll move on to the next one. Okay, this question is, I thought the Forearc Basin was the Strait of Georgia, but I think you mentioned it's wider than that. Can you clarify that?
Yeah, so there's a four-arc basin, which is the Strait of Georgia. That you're correct because it's in front of the magmatic arc that we have, like Mount Meager and Garibaldi and the Cascade Arc that we have on land here. What I mentioned before that was the Foreland Basin, not the Forearc, the Foreland Basin, which is out front to the east of the mountain belt, and it's no longer there. It's the we've had uplift and that seaway is no longer present there. But at about, 150 million years ago to maybe 70 million years ago, or no, a bit younger than that, there was that downwarping in front of the big burgeoning mountain belt that created that seaway. And that was referred to as the Foreland Basin.
Great. Thank you for clarifying that. Just a reminder to everyone that if you do have questions, please feel free to either type it in the chat or use the Q&A function. Um, but let's get to the next one here. Alrighty, so this question is about the tectonic drift of continents. And tectonic drift of continents is due to the internal heat, I assume, and then asking about how different factors affect that activity, and those factors being magnetic pole shifts, radioactive decay, lunar gravity, ice age changes to regional surface pressures, etc. So let me know if you
Oh,
want me to go over that again.
that person's done their homework.
Yes, definitely.
Yeah, so what moves continents, or it's not just continents, it's the tectonic plates in general. So the tectonic plates are the rigid outer surface of the Earth. And it's not all one plate, it's broken up into a bunch of different plates. And those plates are effectively floating on the molten part of the mantle beneath us, what's called the asthenosphere. And so there's a few things that move the plates around. One is the convection within the asthenosphere and the drag that especially the upper part of the convecting asthenosphere has on the overlying lithospheric plate. And so that in part can help to move along these different tectonic plates. There's also the density of, you have an oceanic plate, and as it begins to subduct, in behind, it's pulling whatever's in behind it. It's not leaving it behind. So that's actually a fairly major driver of plate movement is that you have this very dense oceanic lithosphere subducting, and the deeper it subducts into the mantle, the more dense it gets. And so it actually kind of accentuates that pull. And so they call that slab pull or the pull of the oceanic slab going down the subduction zone. Heat is a huge driver and gravity. Those are the two biggies as far as, what drives tectonic plates. And so part of that is radiogenic heat. A big part of it is just the latent heat from the Earth's formation that's insulated within the interior of the Earth and is helping to drive those convection cells, and the densities helping to pull those oceanic plates, and everything that's attached to it and behind gets pulled along with it.
Great. And so our next question, I think, kind of flows nicely from that. It's also about the movement of the Earth's plates, and it just person is wondering that does all this extra active mining activities have any impact on the movement of the Earth's plates?
No, the 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 amount of force, as I showed before, where you're talking about tens to hundreds of trillions of heavy duty bulldozers in that one little area of the Juan Fuca plate. The effect of mining, it's so superficial as far as the overall thickness and mass of the continental plates. Um, it'd be hard to describe, but it's like you're taking a 2 foot thick board and you're laying a piece of paper on it and you're just putting little holes in the piece of paper on top of that 2 foot thick board. It's going to have uh, for the plates, it's going to have no effect on its movement, but there can be local superficial effects for sure. There's been like the Frank slide, that's something that we need to be cognizant of is, on the surface, how is that affecting the stability of the land mass around it?
Great. Alrighty. This question is about how the movement of the tectonic plates, so specifically with Vancouver Island getting millimeters closer to Penticton every year, how is that measured? Is that done with like specific sensors?
hmm Oh yeah, that's great. So GPS, like very high re resolution GPS monitoring. You can also monitor this using satellite information as well. Well, that involves GPS, but that gives us a really precise measurements of, where, say, Victoria is a year ago versus where Victoria is today, compared against where Penticton is situated. And I think I said it's about 7 millimeters closer each year.
Which I think that's so fascinating. It's, 7 millimeters seems so small, but every year that really adds up. That's That's
Sure
crazy.
does.
Yeah. Alrighty, so our next two questions are both about earthquakes. So maybe I'll ask them together and then you can figure out how you want to answer them. So the first one is, do small magnitude quakes reduce the pressure along major faults where we expect a big one one day? And then the other one is, why can't the mega earthquakes be predicted with more accuracy than about 300 to 800 years?
Oh, great questions. Really good. So the first question, yes, those small magnitude earthquakes do relieve some of the stress for sure. Ideally, we have swarms of them and they relieve all of the stress. But unfortunately, it's only little small patches of the interface that stress is relieved from. And some of it is not related to the interface of the Juan de Fuca with the North American plate. Some of it is, related to the strike slip or lateral movement of the Pacific plate relative to North America along the Queen Charlotte fault. So yes, some of those earthquakes do relieve some of the stress, but unfortunately not all of it, and it continues to build up. The second question about uh, why can't we predict earthquakes better than 300 to 500 years? Well, we can. We know that's just the cycle that we know about, that the information that we've been able to gather, or not me, but other people have gathered, have provided a pretty good record of the cycle of those megathrust earthquakes. And so we have like a lot of seismic monitoring and the GPS monitoring, and so we can't predict exactly when the earthquake will occur, but we're getting much better at um, providing a probability, narrowing down the probability of when it will occur. But it's really tricky because it's so far beneath the surface that we can't directly measure. We can't put stress sensors right on that interface and know exactly how much stress is building up and what the release point would be. At what point does it yield and unlock? That's a really difficult problem to address.
Great. Thank you. So if anyone else, oh, I was going to say, anyone else have any other questions? I have one, but we'll get to the, oh, there's tons coming in. Great. Maybe we'll get to mine, maybe we won't. So the next one here from an audience member is it possible to predict and model how the major BC coastal cities will move towards or away from each other in relation to each other over expanses of time?
Yes, yeah. Um, you know, there will be errors in that model just because the Earth and this part of BC is super complicated geologically as far as the plate interactions. We've got the Juan de Fuca plate, but there's also those smaller plates as well that are interacting with the Juan de Fuca plate and the North American plate. And so the adjustments, the movements, um, you know, we can get a pretty reasonable idea from the modeling of, how far or how close the various geographic localities within BC will move relative to each other. That's something we can certainly, get a pretty good handle on. But there's got to be some understanding that there's going to be errors associated with that because it is super complicated and it's hard to predict exactly how all these bits and pieces are going to move relative to each other, through extended periods of time.
Great. Okay. Our next question here is, can you explain the changing dynamics of the EP plate? My understanding is it is not subducting and therefore changing plate movement.
Oh, well, That's not something that I can answer. You caught me out on that. I'm not sure. It is near that transition between where you have the subduction of the Juan de Fuca plate and the um, strike slip motion along the Queen Charlotte fault system. And so my superficial understanding of it, that corner is very complicated, and um, that's best left to, an applied geophysicist to answer.
Great. Okay, so, ooh, every time I'm gonna ask my question, new one comes in. That's okay. Please keep asking questions, everyone. Um, so this question is, what's your preferred risk mitigation measure for the coming mega thruster? How does a rapid inflation helium balloon to lift you above it all sound?
Um, Definitely, we need to be seriously considering, how seismically accommodating our buildings are, especially the older ones. So retrofitting them, identifying structures that are most susceptible. And engineers are really good at this now. Like they've got it dialed in. All of the work that's gone on in California, Oregon, Washington, and up here in BC, they understand. It's just a matter of political will and the money to, you know, allow these retrofits to be put in. Um, Also, a plug for scientists, I think having a society, a population that has some earth science literacy and understanding the hazards, that can occur with say, a mega thrust earthquake, I think would push the political agenda toward being more prepared and to being more prepared as a general population, but also personally, having your earthquake kit always up to date, ensuring knowing what to do during an earthquake, the earthquake drills that we have, all of that is really important. Um, and so I would say overall, just trying to educate ourselves as much as possible, how can we mitigate these risks? It'll be impossible to totally, you know, insulate ourselves from it, but what we can do is be as prepared as possible.
Definitely. And I think that's a good reminder for all of us. If you don't have an earthquake preparedness kit, you should have one on hand, emergency preparedness kit. So good reminder for everyone to make sure you have one and it is up to date.
Mhm.
Alrighty, so I have a question. This is my favorite question to ask during Cafe Sci, to all our presenters is during your research, what is something that you discovered that was a complete surprise to you?
Oh, there's been a lot. The Cordilleran system is super complicated. I think one of the biggest surprises for me is just how mobile these pieces of the Earth's lithosphere, the crust, have been. So, when I told you about that 1/3 of the circumference of Earth is subducted beneath the western margin of North America, that to me, like I hadn't really thought about it. And then one of my colleagues brought it to my attention a number of years ago, and I did the calculation myself. I'm like, is that really the case? And if you know the rate of subduction and you know how long it's been going on for, then you can back out how much lithosphere has gone down the subduction system. Now there's assumptions that it's been continuous and it probably hasn't been. So you know there's a bit of error on that. So that was one big surprise for me, but also related to that was just how mobile these pieces of crust are through geologic time. trying to wrap your head around the immensity of time geologically is really hard to do. Like it's really hard as a human being to think beyond like, 100 years, thousands years, maybe 10,000 years. But when you start thinking in terms of millions, tens of millions, hundreds of millions of years, or even billions of years, a lot can happen. That 7 millimeters of movement, you multiply that by a million years, that's 7 kilometers, right? So a lot can happen in a geological time frame. And so that was something for me, especially when I was early on as a graduate student and wrapping my head around and I knew plates moved around, but just how much and how varied and how complicated it can be. Just an example, take a look at the Southeast Pacific. That is a plate tectonic chaos going on down there. And that's probably analogous to what was going on off the western margin of North America back in, 150 million years ago.
That's, yeah, it's incredible to try and wrap your mind around kind of those
Yeah,
impossibly large things
it,
happening.
it's mind-blowing.
It really is. Alrighty, so I'll just give it a second if anyone else has any more questions. I know we're getting close to our end of our time, but we have time for maybe one or two more if anyone has anything. Oh yes, this is a fun one. So have you reviewed the Clipper mission to Jupiter's moon, Europa, eventually leading to a boring mission into the crust on Europa?
No, I haven't. I've certainly heard about it, but I haven't drilled into it. Part of the fun. Um, I think it's super fascinating, though. If I do have some time, I think I will. You know, Especially as they get closer to doing something like that, I will. Turn my focus on that because that is a super interesting topic for sure.
Yeah, I can only imagine just the differences and similarities that must exist out there.
Yeah, well, Earth is a very unique planet, especially in our solar system. It's the only one that really has like what we would consider to be like plate tectonics going on. Um, all of the other planets and moons in the solar system, they don't have the tectonic processes that we have here on Earth. They have different sorts of movements, especially vertical movements and things like that, but they don't have the big scale horizontal movements of plates.
Right? Alrighty. Well, if we don't have any more questions, I think it's time for us to wrap up for this evening. Um, if somebody does think of something that they really need an answer to after we close out, just please feel free to send me an email and I can get in touch with Dan and we can find an answer for that. Um, so unfortunately, this is now our time to say goodbye. But first, huge thank you, Dan. Thank you so much for spending your time with us this evening and sharing your incredible research. And I hope now, as we kick off our summer road trip season, everyone will drive, through the beautiful BC mountains and take a little bit more knowledge with them about just kind of how incredible they really are, not just visually, but everything that's happening underneath. So thank you to Dan, and thank you to all of you who joined us here this evening. Like I said, this is our last Cafe Sci until September, so please enjoy your wonderful summer road trips, and I look forward to connecting with you all again in the fall.
And thank you for having me.